All right, welcome to Systems and Controls again. I'm your host. Yeah, I think my lectures are getting more increasingly boring as the content gets more increasingly boring. So, it's for you. What we briefly introduced last time was the idea of a matrix. We had a giant system of equations. All of those are solvable. I ended up putting all their coefficients into a matrix. I talked about how to multiply. That serves as kind of our segue into discussing matrices. Linear algebra, the term linear algebra is pretty much commonly used to describe matrix math. The idea is that matrices are themselves linear entities, and because you have linear entities, linear math, the solutions to those problems are pretty nice. The whole goal behind using matrix math is that if I have a matrix multiplied by a vector is equal to another vector, which is what our solution was last time. What I can do is I can solve this system for, first of all, whatever vector this is, but I can also solve this system for whatever b is, because b is equal to the inverse. Now you just divide it by a, both sides, or multiply it by the inverse of a, which is what matrix math is used. Okay, and this is the ultimate solution. This is what we're trying to find. And what we're going to be discussing in as far as matrix math goes is we're going to be discussing the principles that we need to take this equation where it's some matrix multiplied by the variables equals some outcome, and switch it so that some variables are equal to whatever the outcome is multiplied by the inverse matrix. And this will be, it's a really powerful tool in math to be able to use matrices to solve systems of problems. We'll go ahead and get started. You will have a number of problems related to matrices over the next 2 weeks. I am going to give you homework over matrices, so do keep that in mind. The reading assignments, in my opinion, go really... This is going to be the second lecture I was going to give with a mask on. The reading assignments go pretty quickly, so it's not something where I'm terribly afraid that I'm overwhelming you with too much work. I do want you to be continuing to focus on the construction of your light boxes. Most groups are making good progress, but we're nowhere near where I was hoping to be at this point in the semester, so that happened. Some of this, it doesn't help that we're in a hybrid format and I only see half of you once a week. So if you want to show up both Tuesdays and Thursdays and work on your project, you're fine. That actually is doable. We do have enough classroom space to be able to handle that, so long as one person doesn't show up. So if too many people show up, I'll kick one person out. Yay, university restrictions. So the ultimate goal of doing matrix math is we want to be able to solve our variables. We want to be able to switch variables. And we have talked about using Laplace as a method of developing linear problems. Now we're going to be discussing how to use matrix math as a way of taking those linear problems and creating a solution from them. So, I guess let's jump into it. A matrix is usually defined by a bold capital letter, okay? So drawing this bolded is bold. That signifies that it's a matrix. Other ways that people will do it is they will draw two lines underneath the matrix. Sometimes they will do it on top, but all three of these signify that whatever A is, it's a matrix. Okay, this doesn't require bolding letters, so this is sometimes what handwriting does for signifying a matrix. So these are matrix notation. Similarly, if you have a little a, and you put one of these on top of it, you could also have little a and have a single bar underneath it. And some people will have little a and they'll do like a hat thing on it. This signifies a vector. Okay, so what is a matrix? The definition of a matrix is it's just an array of numbers. Okay? The matrices that we're going to be dealing with in this class are 2D matrices, which means you have 2 dimensions to it, columns and rows. But technically you can also have columns, rows, and then depth. And you can go into 4D matrices. Those are a little bit gross to deal with. You can even do that in Python. It's pretty sweet. We are going to be doing some matrix math in Python, so just make sure that you've got the ability to do some Python somewhere. You can pull out your Raspberry Pi and do it on there. I personally like doing that. And we're going to be discussing just Python matrix evaluation. I'll pull up my Pi and we'll do some calculations there. So, all right, so that's what a matrix is. A vector is a one-dimensional matrix. Okay, that's what it is. That's one definition of it. It's a singular column of numbers. Now, vectors are always one-dimensional, whereas a matrix, usually the ones we're going to be dealing with are two-dimensional. Vectors are always one-dimensional. So there is some distinguishing there, okay? These are vectors, these are matrix, so let's go ahead and do it. When I draw a matrix can have any number of, these are your rows, and these are your columns. Okay, a matrix can have any number of rows and columns as you want. Now there are some issues that come about if you have weird numbers of rows and columns. We won't talk about those yet. I think that's either a next week thing or a 2 weeks from now thing. And anyways, these are your column numbers. So if you have 1 0 1 0, you've got 4 columns, and this is all in one row. And you have 2 0 2 1 and 0 1 1 1. This matrix here has 3 rows and 4 columns. So this is a 3 by 4 matrix. When signifying the dimensions of your matrix, you always start with a row number first, followed by your column number. Okay? This way first, followed by this way. That's just typical convention. Okay, when you're talking about a vector, you remember a vector is only one dimension, which means it only has one column. It's always going to be a something by one matrix. And you can have as many numbers as you want in here too. Let's say we're just going to do 1 0 1. So this would be a 3 by 1 vector. Okay, really simple. Now let's get into fundamentals of what's needed to add and subtract matrices or vectors. Addition and subtraction, this is pretty straightforward. Here, we talked about it briefly last time. I didn't go nearly in enough detail. But a 3 by 4 matrix, if A is equal to a 3 by 4 matrix, and B is also equal to a 3 by 4 matrix, then A plus B exists. You can't add matrices that don't have the exact same number of rows and columns. this has to be identical, and this has to be identical. Otherwise, you can't add them. If C is equal to 3 by 4 and D is equal to 3 by 5, you cannot add them. Okay? It's just the nature of matrix math. You have one weird column that's just sitting out there that gets added to nothing. And it doesn't make any sense. And we did discuss that in the last class. So in addition and subtraction, you can add them, you can subtract them, and then what you do is you go in to each individual element and you add and subtract each individual element. So if my A matrix is equal to 1 0 1 0 1 0 1 0 1 0 1 0, and my B matrix is equal to 3 3 3 3 2 2 2 2 0 0 0 0. Okay, then A plus B is going to equal 4 3 4 3 3 2 3 2 1 0 1 0. Okay, each individual element adds together or subtracts together to result in your solution. So addition and subtraction, that's pretty straightforward, but they do remember that you cannot add matrices that do not have the same number of rows and columns. So it's always a good idea, whenever you have a matrix, the first thing you're going to want to do is establish what are the dimensions of that matrix, because that'll say what kind of processes you can do with it. Okay, next we're going to look at what's called scalar multiplication. In scalar multiplication, let's say I have some constant c. C is just a single scalar value. Okay, and let's say I have A, which is some matrix. I'm going to go ahead and make this be a 2 by 5 matrix. Okay, then CA is going to be equal to, this is C times A11, which that's the first row, first column, C times A12, C times A13, C times A14, C times A15. That's really how it works. You multiply this scalar value by every single component in here. So this becomes C times A21, C A22, C A23, C times A24, and C times A25. So if my A vector is 1 0 1 1 1 1 2 2 3 1, okay, and my C value is equal to 3, then C times A is equal to 3 0 3 3 3 3 6 6 9 3. Okay, each individual value is multiplied by this single scalar C, and that's what this shows. Every single value in the matrix, where this is A11, this is A12, etc., gets multiplied by C. Okay, so that's scalar multiplication. Again, pretty straightforward. The crazy part of matrix math comes when you want to multiply matrices by each other. Multiplying matrices by each other is kind of a tricky process. Okay, so when you go to multiply matrices by each other, let's say A is a 2 by 4 matrix and B is a 4 by 4 matrix. Okay, now you cannot add A and B together. You just can't, because they don't have the same number of rows. So that condition, you can't add them, you can't subtract them. However, when it comes to multiplication, what matters is, does the number of columns in the first vector equal the number of rows in the second vector? Okay? If that is true, then they are multipliable. Now, be careful with this, because this is not possible. You cannot multiply B by A. Here, A is a 2 by 4 matrix, and you're multiplying it by a 4 by 4 matrix. These two numbers are the same, you're good. If we switch that around to try to multiply B by A, this is a 4 by 4 matrix multiplied by a 2 by 4 matrix. These two numbers are not the same. That's not okay. So, in matrix math, unlike in other kinds of math, the order of your matrices matters significantly. Okay? This is no longer something where we can just simply say, well, 3 times 4 is equal to 4 times 3. That is true in scalar math. That is false in matrix math. It's just the nature of how this is defined. So this is a common pitfall that happens among a lot of young mathematicians and a lot of young engineers. You cannot have these two, they do not equal each other. They're not the same thing. This one doesn't even exist. Okay? So when you multiply vectors by each other, here we can multiply A and B. If A is defined as A11, A12, A13, A14, A21, A22, A23, A24, where each of these values is just some scalar value. It's 1, 5, 7, 9, whatever. And then B is B11, B12, B13, B14, B21, B22, B23, B24, B31, B32, B33, B34, B41, B42, B43, B44. Okay, so that's my two matrices. When I multiply these two together, the matrix math itself gets a little bit wild. Because my end result, if I say AB is equal to C, where all three of these are matrices, first of all, what this means is I have 2 by 4 multiplied by a 4 by 4. These two are the same, so my resulting matrix is going to be a 2 by 4 matrix. Okay, so C is going to be a 2 by 4 matrix. Okay, my resulting matrix is going to look like this. I will take every value in this row and multiply it by every value in this column. And then I will do the same for every single column. It's kind of like the term indexing. I'm multiplying by this column and this row, so the result is going to be a single value that is in that column and that row. So C, the values for C are going to look like this. It's going to be A11 times B11 plus A12 times B21 plus A13 times B31 plus A14 times B41. Okay, so it's this value times this value, this value times this value, this value times this value, this value times this value. And that is the first entry in C. I then have to do that 3 more times. And then my next one, it's A21 B11 plus A22 B21 plus A23 B31 plus A24 B41. Okay, so then it's this row multiplied by this column. Then the entry next to it, this dot over here, is this row multiplied by this column. Then it's this row multiplied by this column. And it's this row multiplied by this column. So all 4 of those, which I ran out of board space, also ran out of interest. All 4 of those, that's how you do matrix math. matrix multiplication is kind of gross. Now, there is a tool available to you. So I have no idea. Just had some weird internet thing happen, so I don't know how much of that video just got cut off. But yeah, it says it's good, so I'll see you next week.